So we looked at pressure-volume relationship, so-called Boyle's law, PV equals PV, one set to another, P1 V1 equals P2 V2. That's if you change one variable, keep temperature and the number of moles constant, you can use this formula. And we looked at Charles' law, which looks at temperature and volume. Oops, that's like this. V over T equals V over T. And if you put them together, you come up with the combined gas law. You can actually have all three variables, so now you just have to hold the number of moles constant, meaning you cannot add or subtract, take out the amount of gas you have, and you can have P1 V1 over T1 equals P2 V2 over T2. And of course, if you then hold temperature constant, you can get back to Charles' law, or if you keep pressure constant, then you can get back to Boyle's law. Okay. Sorry, Charles' law is this, Boyle's law is this. Not all that drastically important. Okay, and so then we can work problems with this. A 10.5 mole sample of oxygen has a volume of 25 milliliters. So we've got 10.5 moles. It's at 25 milliliters, and it has a temperature of 23 degrees Celsius and the pressure of 243 torr. So you have all four variables that here, right? And then the question is, what would the volume be at 0 degrees and 760 torr? Well, it doesn't make any mention that the volume here, or not the volume, but the number of moles have changed. So we are going to assume that that's not changing, and that's just there to confuse us. So, and so we can write all our variables down. We can say we've got an oxygen gas, and that's going to be irrelevant, but we have a volume of 25.6 milliliter. And that volume is at a temperature of 23 degrees Celsius. But we do need to change that to Kelvin, so we just add 273 to it and get 296 K. So that's also T1 here at a pressure of 243 torr. And you can keep that pressure with that unit. You don't have to convert that. And that's 243 torr. And then we're told, what would the volume be? So we don't know what V2 is. At 0 degrees, so the temperature here is going to be 273 K. That I changed already at a pressure of 760 torr, right? So all you have to look at now is that, okay, so the pressure is at torr. Those two will cancel. And then you take P1 V1 over T1 equals P2 V2 over T2, this formula here, and you solve for VF, right? So you divide by PF and you multiply by T2. And when you write all that out, you get that VF. I'm going to do F equals, I should do it here. This is 2, 2 and 2. This is of course also 2. Sorry about that. So we're going to do V2. V2 equals P1 V1 over T2. No, not over, but times T2 divided by T1 times P2. Plug it all in, you have 243 torr times 25.6 milliliters times 273 K, right? So that's T2 here divided by T1, which is 296 K, times the second pressure here, which is 760 torr. And I've written all these units. I think it's important that you see, okay, torr cancels here and that Kelvin cancels, and that whatever my answer is going to be in milliliters. And since I don't really specify what unit I want that volume to be in, you can just put that in the calculator and you will find that there's 7.5 milliliters is the new volume. Okay. So that's not a big deal, right? Okay, here it is all worked out nicely. Let's take a look at another gas law that involves the number of moles. And that's Avogadro's law. Now, Avogadro's law states that equal volumes of any two gases at the same temperature and pressure contain the same number of molecules. Let's take a look at that. Okay, so what this gas law says is that no matter what your molecular weight is, whether it's 58 or 2 or like xenon gas, which is 131, that all of those gases occupy the same volume at the same temperature and pressure. Now, how does that make any sense? It certainly has a different mass, right? We would expect intuitively, possibly, right, for xenon to have occupy maybe a larger space, right? That's not necessarily a bad thought, but if you take into consideration what makes something a solid or a liquid, and those are the so-called intermolecular forces, which will be covered in detail in chapter 11, but we already know one intermolecular force. It's called the hydrogen bond here, right? And so you have this force that's holding two water molecules together. In fact, you know you have an entire network, and the same is true for any of the liquids or solids. They're held together. And even water, when you take it to the boiling temperature, which means you are breaking this intermolecular force with the thermal energy you're sticking in there, there's no reason why this oxygen cannot now travel unless it's contained in a vessel. It can travel far away. If you think about boiling water, you see the steam and then you don't see it, and it spreads out, right? And so if there's nothing holding these two molecules together, they're going to go as far as possible as they want, right? Because, every now and then, and so they have kinetic energy, they bounce around, and the same thing is true for xenon, hydrogen gas, any of these in the gas phase. So the distance between them is so large that their size is negligible, right? It doesn't matter what the size is. This can be this big if the distance between them is really large, or they could be this big. And if there's the same distance between them, then something that is super small and something that is super large is going to occupy the same volume. And that's why we have Avogadro's law. So xenon gas and hydrogen gas, if they are at the same temperature and pressure, occupy the same volume. And it turns out that that volume at STP, now that's standard temperature and pressure, and you would do well remembering what that is. It is 1 atm and 0 degrees Celsius, or 273 degrees Kelvin. Those are the standard temperature and pressure. And so at that pressure, 1 mole of any gas occupies, and there are slight discrepancies, but for the most part, 22.4 liters. Okay, so that's kind of like a 5-gallon bucket. So that's this. So 1 mole of hydrogen occupies 22.4 moles. One mole of oxygen as well, right? And so we can translate that directly to these molar coefficients. If you remember here, this reaction, hydrogen gas and oxygen gas making water. See, these are all in the gas phase here. So you have 2 moles of hydrogen required for every 1 mole of oxygen. And so you can actually, since this is in the gas phase, now say, well, if I have 2 liters of hydrogen, then I need exactly 1 liter of oxygen. And that, when I combine those, I am going to get 2 liters of water gas, right? As long as everything is in the gas phase. And it doesn't even matter whether we have STP or anything, as long as we have equal volumes, the ratios of the volumes equal the coefficients here, right? We can do that. We can say, well, if it's 20 liters of hydrogen gas at any temperature will react with 10 liters of oxygen gas at that same temperature to form 20 liters of water. Or if you would like to do this on a molar scale, you would then simply say, well, as long as we then are at STP, if we have 48, sorry, it's 44, 22 times 2 is 44.8, 44.8 liters, which would be at STP exactly 2 moles. That means we need 22.4 liters of oxygen. So that would be on a molar scale. So just that you understand that, right? So just to get the point across here, if we pressurize a vessel here, a balloon, with here we have ideal gases here, helium, xenon, and methane. So at those temperature, well, xenon and helium are ideal gases. Methane is not, but methane acts as, because the intermolecular forces are so weak that at STP it is a gas, and they all occupy 22.4 liters, and no matter the size difference here is not all that, doesn't look all that drastically different, but the mass is fairly different. The point is again that 1 mole of any substance at STP will occupy any gas, right? And even water, as long as you keep it in the gas phase, except you can't at STP. And so there are some slight discrepancies here, right? So we have helium, hydrogen, oxygen, carbon dioxide, ammonia, and just ideal gas in general, but you can tell here that these are very close. They're just very slight discrepancies. Between 22.1, so to speak, and 22.4. So there's just small differences in volume. Okay, so that's Avogadro's law. And if we take Avogadro's law and Boyle's law and Charles' law and we put it all together and we put the number of moles in there as well, we come up with a formula called the ideal gas law, where PV equals nRT, where n is the number of moles. And I don't want to go into any great detail here. You'll have access to this formula, but it relates all of the empirical gas laws here: Charles' law, Boyle's law, and Avogadro's law, and it puts it all together. And so of course this formula then applies not for a change in conditions, it's for solving for one variable, right? So if you have a gas, you measure pressure, volume, and temperature, you can then calculate the number of moles. Or if you know the number of moles, volume, and temperature, you can solve for P and calculate that, right? So there's also something called the ideal gas constant, which we will look at here in a second. And then of course these are all related to, if you take PV equals nRT and you solve for nR, or so PV over T equals nR. This is just, it's not all that important, but let's just, if you call this condition number 1, and then you say, well, we can have a second condition, P2 V2 over T2, and we also set that equal to nR, and R's the same, it's an ideal gas constant. As long as we keep the number of moles constant, we can set these two equal, and so this is how you can get back to the combined gas law. So in any scenario where you're actually taking an exam without the book, you can then memorize PV equals nRT and derive by just doing some simple algebra, putting the T over here. And setting it equal, you can get back to the empirical gas law, right? So that's not a real big deal. So the ideal gas law is PV equals nRT, pressure times volume equals number of moles times an ideal gas constant times temperature. And so the ideal gas constant can of course have different units and therefore different quantity, but for the most part we're going to use 0.082058 or a 0.0821 probably for most cases is enough. That has 3 significant figures: liters times atmospheres divided by Kelvin times moles. Alright, so when I have variables and I use this ideal gas constant, I need to make sure that my temperature is in Kelvin, this is in moles, this is in liters, and this is in ATM. So for this we have to convert. everything to those units that are equal to the units of the ideal gas constant, right? And so if I ask you a question here, we're going to use PV equals nRT. I'll provide you with the ideal gas constant, or you can provide yourself with the ideal gas constant. And I ask, an oxygen cylinder has a pressure of 20 atm at room temperature. So we know temperature, we know pressure, and a volume of 4 liters. Okay, let's say 4.00, just to, well, it doesn't matter because we have technically one significant figure here, 2 there, but so 4 liters. How many grams of oxygen are contained in the cylinder? So the only problem here we have are the grams. That's not part of the ideal gas constant, but we know very well that the number of moles is related to the number of grams, and that's because molecular weight is equal to the number of grams over the number of moles, right? And so we do know what that is for O2. We know that the molecular weight for O2 is 32 grams per mole. And so what we can do is then we can take this formula, molecular, because this is really N, right? So what we have is molecular weight equals mass. Let's just call that little m divided by N, which is the number of moles, right? And so we can solve for N. So N is going to be equal to m divided by molecular weight, right? I brought this over here and then I divided it. Just a little bit of algebra. And so then I can take that N and replace that in this formula. So what I get is PV equals m over molecular weight times R times T. And then I can solve for, let's see what they're asking for, how many grams. So I actually solve for grams here, right? So I'm going to solve for m. So m is going to be equal to PV times molecular weight divided by RT. So that's just some basic algebra. So now I can plug in everything. And so I'm given 20 atm. I'm not sure I'm going to squeeze it all in here. 20 atm times volume, which is 4 liters, times the molecular weight, that's 32 grams per mole, divided by the ideal gas constant, which is 0.0821 liters times atmospheres divided by mole times Kelvin. So right away we can see the liters cancels, the atm cancels, and the moles cancel. And I am multiplying by, of course, 21 degrees has to be added to 273 because we have to have Kelvin here, right? We want Kelvin to cancel, times 294 Kelvin. That cancels, and we get an answer of 106 grams. So of course that's just 100 to one significant figure, but I'm just going to leave that be at this point, right? And so you need to be able to, if you don't remember your algebra, but you should need to be able to do that, and you need to see the connection between number of moles and mass. Another thing I can do to this is ask for density, and so you can also figure out density by using the ideal gas law, right? Anyway, this is just what we just did, all worked out. But I could also ask you, what is the density of helium gas in grams per liters at 30 degrees and 0.950 atm, right? So if I'm asking for density, I need to know mass over volume. Okay, so I can use the ideal gas law to solve for volume. Okay, so let's do that first, and then see how we can figure out the grams of helium, right? Okay, so I use V equals N times R times T over P. Okay, Okay, well, I don't know N. Huh, interesting. Okay, so I can actually make up N, right? Because I know the substance and I know that density is independent of quantity. So 1 mole of helium has the same density as 2 moles of helium. 1 gram of helium has the same density as 257 pounds of helium. So I'm going to make my life very simple and just make that 1 mole. So if I use 1 mole, and that solves my problem of mass, right? Because now if I have 1 mole of helium, I simply go to the periodic table, so I know my mass is going to be 4.003 grams. So that makes my life much easier. Then I plug in the ideal gas constant, 0.082058. I'm going to keep them all just for the heck of it, times ATM divided by K times mole. And then I multiply by T, and T is 30 degrees, so I add that to 273, which makes that 303 Kelvin. So Kelvin cancels, moles cancels. We have liters atmospheres. Of course, we know we want liters, so I'm going to divide now by P, pressure, and it has to be in ATM. It's given to me in ATM, so 0.950 ATM. That gives me volume, so I'm going to write it over here, and that volume is 26.2 liters. Now that I'm going to take and plug it into here because I'm asking for density, right? So density is going to be equal to 4.003 grams divided by 26.2 liters. And that gives me a density of 0.153 grams per liter. Okay, and that's what I'm asking for specifically in grams per liter. 0.153 grams per liter is the density of helium gas at these conditions. And again, it's independent of the amount of helium that if we have more, we are simply going to have a larger volume. So you can just calculate that for half a mole or a gram or 5 grams. But this is probably the easiest, right? So here I have that problem all nicely worked out. There are several in the in the book. Let's do one more, okay? So here we have calculate the density of nitrogen gas. A very similar problem here, right? So we have to calculate the uh, density of nitrogen gas at 125 degrees Celsius and a pressure of 755 millimeter mercury. So I'm going to do the same thing. I'm just going to use 1 mole of nitrogen, and then you need to remember that nitrogen is N2. That nitrogen is diatomic. In fact, all those gases, N2, F2, Cl2, O2, H2, those are all diatomic, and so nitrogen gas is not N. Nitrogen gas is N2. Very important. So I'm going to use 1 mole, and 1 mole is going to have a mass of 28.02 grams. That's going to be equal to 1 mole. Okay, so then all I need is the volume. The volume is going to be equal to 1 mole times ideal gas constant 0.0. I'm going to do 8 to 1 to save myself a little bit of space here. Liters times atmospheres per K per mole times 398K. See, I had to convert 125, add that to 273 to get to 398K. And then I divide by the pressure, and I have to convert the pressure. There are 760 millimeter mercury in 1 ATM, so I divide that by 760 to get ATM, and so it's 0.993 ATM, which is going to equal 32.9 liters. And when I plug that into here, I actually, oops, okay, yeah. Okay, cool. I have that down here. So lucky me, right? So there you go. So then the density is going to be 0.851 grams. Okay, that's enough. 25 minutes is enough. And I'll see you in a little bit.